This lecture series is going to be about the general question of understanding the emergence of bulk physics in AdS CFT from the quantum mechanics point of view. Today will be the sort of preliminary lecture. I'll review some fairly standard things about bulk reconstruction, which is a thing I'll define in AdS CFT. So actually, probably for experts like Subrat, this will be the most boring lecture, so sorry, Subrat. Yeah, let's start. So what does AdS CFT tell us? It tells us that quantum gravity in AdS is dual to conformal field theory on the boundary of AdS without gravity. So, and to be a little bit more precise about it, right? It says that sort of asymptotically, AdS quantum gravity, AdS d plus 1, is CFTD on r times SD minus 1. So for the most part, we'll always be discussing this version of the correspondence, the global AdS correspondence. So what does this really mean? This equal sign in the middle. Well, here are a few things that it means. So it means that states in the quantum Hilbert space of this theory are in one-to-one correspondence with states of the CFT quantized on a spatial sphere. And then we know that those are in one-to-one correspondence with local operators in any conformal field theory. Symmetry generators, like the Hamiltonian, the angular momentum, any internal symmetry charges in the bulk, act in representations on this Hilbert space, and then, via the duality, it's the same Hilbert space. And so they're going to be dual to operators that act in the same representations in the CFT. And so here, these are global symmetries of the CFT. And here in the bulk, these will be asymptotic symmetries, which are associated to gauge symmetries in the bulk. And then finally, for our purposes, perhaps the most important. So we talked about the states and we talked about the symmetries, but well, these are some operators. This is some operators, but they're not the only operators that we're interested in. This is quantum mechanics, and there are all sorts of observables that we could be interested in studying. So the simplest thing we can do, it turns out, is to do a limiting procedure where we take the limit as we approach the boundary of a local field in the bulk, rescaled by the radial coordinate in some way, or more inherently by the sort of scale factor of the boundary metric. And then in the CFT, we get a local operator. So if we take a local operator in the bulk and we pull it to the boundary, then we get a local operator in the CFT, and this is an operator equation. I guess so far no surprises. So this is an operator equation, if you like. It's saying that in any state in the CFT, this local operator has this interpretation in the bulk when we think about the bulk theory. Now, this version of the dictionary, so this is usually called the dictionary. So this version of the dictionary is good.
Sorry,
yeah.
Asking. In the last line on the left-hand side, is phi a bulk free
yeah.
operator?
It's a field. quantum field. So we're always going to be doing quantum mechanics in the bulk. So to me, classical physics in the bulk is boring to me. I want to do quantum field theory in the bulk. Yes, this is an operator equation. Okay. So this version of the dictionary is sufficient for thinking about what you might call scattering experiments. So say, for example, you want to make some stuff at the boundary and send it into the bulk, and then maybe something happens, and then we see what comes out. And so this kind of transition amplitude kind of physics via this sometimes, I guess Douglas Stanford and I call this the extrapolate dictionary. It seems like a good name for it. You extrapolate a bulk field and you get a boundary local operator.
Sorry, so in this last line again,
Yeah.
Isn't there some Legendre transformation between in this correspondence? Because
No.
phi is supposed to be like the source for all.
Yeah, that's the old so there are two different ways of thinking about the operator dictionary.
Yeah.
So there's another version where you imagine taking a CFT and turning on backgrounds for operators. I don't want to think about it that way because I want to work in the Hilbert space of the CFT with no sources. So I want to talk about operators in the original Hilbert space. And so if you translate that version of the dictionary into a statement about operators in the original Hilbert space, then you just get this equality.
The classical version for this is that the normalizable part is the expectation.
Is the expectation.
Yeah,
But
that's right. That's right.
The normalizable part.
That's right.
Set the non-normalizable part to 0.
Yeah, you're right. You can say I set the non-normalizable part to 0, like because there are no sources, and then the vev of this is the vev of that, right? So often this equation is stated as an expectation value, but that's a very weak way of saying it. This is a much stronger statement. It's also true.
It's also true, except for the fact that really there are no operators in the bulk.
Well, we're going to discuss that. But so in the limit that they approach the boundary, they become better and better defined. But indeed, the whole point of the lecture series is to understand how we think about the left-hand side of this equation, especially when we don't take the limit as r goes to infinity. Okay. So yeah, indeed, I was about to discuss that. So using this statement of the dictionary, we can immediately take these kind of scattering kinds of questions and reformulate them in terms of correlation functions of local operators in the CFT. So any experiment that you can ask about by this kind of thing, this dictionary already is good enough to ask about it. And so for a while, most people were satisfied with that. But sometimes there are experiments we want to do where we don't know how to ask about them using these correlation functions of local operators in the boundary theory. So one simple example of that is, say we've got an AdS Schwarzschild black hole, and we say we send in something here and something here. They evolve in. One of these scattering things happens here, but then whatever comes out ends up in the singularity, and so it doesn't make it back out to the boundary. So then, if we want to ask about, what do we expect for these kinds of transition amplitudes or experiments? We don't know how to describe it just using this line of the dictionary. So somehow what we want is to be able to directly ask about what's going on in here without having to be able to evolve it necessarily back out to the boundary. So as usual, right? Kind of this is the kind of problem that we would like to solve, but that one's kind of hard. So what we'll do first, and actually spend most of the lectures doing, is understand how to think about what's going on here without evolving things out back and forwards, and then hopefully once we understand that well enough, then using similar techniques we'll be able to think about this kind of thing. And actually, in this particular case, we do know how to think about it. There in the specific case of the thermal field double and sending these things in, without any, without having them coming too far in the past and so on. Okay, so what we'd like to do is is to understand phi of r, t, and omega without the limit. We'd like to not take that limit as r goes to infinity. This is some operator in the bulk theory, and we'd like to understand how to represent that operator on the Hilbert space of the CFT.
So, can you just explain this?
Yeah. This one?
Yeah.
Okay. Well, so one simple version of this experiment is we say we don't even send anything in, and then we just ask, or maybe we can think of you have an experiment where we go in here, and then we ask, okay, 10 seconds after we cross the horizon here, what's the probability that we see a proton? That's an experiment which we can certainly do. I mean, if someone comes to you telling you that they have a complete theory of quantum gravity, then they better be able to answer that, to give you the probability.
What was the question again? Sorry.
Well, I jump in here, and the question is 10 seconds after I cross the horizon, what's the probability that I detect a photon, or a neutrino, or an elephant, or whatever. I mean, if we can't answer questions like that, then I would say we don't have a theory of quantum gravity that really, makes predictions for all the experiments that we can imagine doing. Okay. So what we'd like to understand how to think about these operators in the bulk without taking the limit. Now, there are some issues with trying to do that. Right, so as Shiraz already sort of indicated. Let's discuss sort of the two complaints which probably most of you are already thinking. So the first one is that phi is not gauge invariant. Right, so in the bulk we're doing quantum gravity, so we shouldn't really have local operators. So indeed that's true, but this is kind of but it turns out this is kind of a more, at least so far it seems, a sort of technical problem rather than a problem of principle. So as with electrodynamics, the way you deal with this is that the gauge invariant operators you're really interested in aren't quite local operators. They have some sort of dressing attached to which attaches them to infinity. So for example, in electrodynamics, you're never really interested in, say the electron field sitting here. That's not a gauge invariant operator, but you can attach a Wilson line to the electron field which runs off to infinity, and that's a gauge invariant operator, right? And so then when you act in the vacuum with that operator, it creates the electron together with the electric flux tube which satisfies Gauss's law. It's not unique how you do this, right? You can run the Wilson line this way, you can run it that way, you can choose something that's more spherically symmetric than having a flux tube pointing in one direction. And these are all different observables. Different observables in electrodynamics. Similarly here,
Can I just, sorry,
Yeah.
you probably say this so slowly, but also can't we use large n, that is strictly in the n equals infinity limit where the metric doesn't fluctuate.
yeah.
There we can just use the background metric as a partial define.
Yeah, so
The extent it fluctuates, all right, then there's
Right.
a line scale fuzz in the.
Right, but most of the quantum mechanics is happening in order g to the 0, and so I wanted something that works to all orders of G-unit perturbation theory. So you're right that if we literally only work to leading order, then it's like quantum field theory in a fixed background. But I don't want to be restricted to just dealing with
I mean,
that.
in our room here, we talk
Yeah.
about local operators, right?
Yeah, yeah.
And,
Yeah, that's
it's a
because
good
we're working to
approximation.
leading order in G-unit.
And then
Yeah.
we can, but if you really want something which is absolutely precise, then is the notion of this dressing well enough defined?
Yeah,
You
so-
could say, I'm going to fall in and wait for so much proper time.
Yeah, that's right. That's the kind of
that
thing.
kind of
Yeah.
thing,
Yeah.
and-
So to all orders in perturbation theory in G-Newton, these operators are well defined. So it cannot, like a simple thing you can do is you can say, I start at the boundary at some particular point, and I shoot a geodesic, which is orthogonal to the boundary, in for some fixed or normalized geodesic distance, then I just put the operator at the end of it. So that's the gravitational analog of the charge with the Wilson line attached.
And then if the metric is fluctuating, that geodesic has to be chosen. If I'm doing some path integral,
Yeah.
I have, each metric I'm integrating over, I choose
Yeah.
the distance for that.
That's right. But it's no more mysterious than the Wilson line. You know what I mean? So, I mean, one way of seeing that is if you work in so-called holographic gauge, or Pfefferman-Graham gauge, it's called for gravity. For the gauge field, it's like AZ equals 0 gauge. And then you just write down the operator in that gauge, then it ends up being this one if you sort of make it think about it as being gauged in the gauge invariant way. So, yeah, I mean, that's just a choice. I'm not saying that dressing is better than any other dressing. It's one that sometimes it's easy to calculate with. But just any time we try to reconstruct an operator, we're, at high, beyond leading order and perturbation theory, part of doing that is saying which gauge invariant operator we're talking about, and that includes the dressing. So every argument that I'm going to give throughout this lecture series can be made being careful about the dressing, but I won't always be careful about the dressing. So sometimes I will be if it's especially important to think about it at that particular point. But for the most part, I'll just sort of not discuss it explicitly, and then if somebody complains, then we can get into it for that particular case. Okay. So this is not too bad. So we have to be careful about it, but okay, we can be careful about it. A more serious objection to trying to talk about phi is that the bulk is emergent, and entropy scales like area. So there can't really be a volume's worth of degrees of freedom in the bulk. There can't really be independent sort of phi operators at every point in space, or including the dressing if we want to be careful. Somehow there really have to be a lot fewer degrees of freedom in the bulk. So that's got to put some limit on the validity of trying to talk about operators like this.
Is that related to the fact that there is a very large diffeomorphism symmetry in the bulk?
You mean just the GR diffeomorphism? No, I would say that's point one. So if we define the operator as gauge invariantly, then we've dealt with the diffeomorphism invariance. The diffeomorphism symmetry isn't enough to get rid of a volume's worth of degrees of freedom, right? I mean, morally, it's just electrodynamics with another index. So the gas of gravitons or whatever, it still has an extensive partition function. You just throw out a couple of polarizations.
Now in AdS, volume and area scale the same way.
Yeah, but it's where the ends go is the difference, right?
But is what?
It's where the ends go. So that's true above the AdS scale, but this equation is in Planck units. So the ends are different. Yeah.
Just go back to Svenka's question, if I
Yeah.
may. I mean, since we are doing quantum gravity, not just Einstein gravity, which we tried to quantize,
Yeah.
it's true that string theory probably has some much larger set of symmetries.
Oh, that's true. Yeah, that's true.
Could it be that when you incorporate all of them, in a sense, you find that
Well, that might be true in some deep non-perturbative sense. Yes, I just meant that it's not going to be true in the trivial sense where you look at the diffeomorphisms of Einstein's theorem. I mean, the gauge symmetries sort of don't mean anything anyway at some level, right? So
And sorry, just coming back to one other thing. The kind of thing that you talked about, these local operators, which you define by shooting something from
yeah,
a well-defined infinity,
yeah,
one could try to do that in flat space as well, right?
yeah.
So with that definition, you have some diffeomorphism invariant local operators in flat space theory.
Yeah, they're not really local. I mean, their algebra with the other operators, it detects this string or whatever.
Fine. So you could imagine trying to set up a calculation of correlation functions of these operators.
Yeah, that's right.
However, in string theory, we're never able to do such things.
Well, I
Doesn't
don't know.
suggest that-
I guess Ashok thinks he is able to, right? You know, I mean, it's ugly, but
But it's all, I mean, unless it's an S
I mean,
matrix, it's all gauge dependent.
Yeah, yeah.
yes, but gauge dependent, and that's part of what we're talking about, right? So when you, right? I mean, if you pick a gauge and then you say I'm looking at this operator and that gauge, that is actually a gauge invariant operator. It's just that its presentation looks different.
It's diffeomorphism invariant. I was just wondering whether,
Yeah.
when you take into account all the symmetries of string theory,
Yeah.
it could still be invariant.
Well, yeah. Again, we have to discuss whether we're asking for things that are really precisely defined
Yeah.
at at finite n, and things that are somehow only true in some expansion of integer.
Right.
So at best, for this kind of thing, we're going to expect that things are only well defined up to order e to the minus 1 over g.
So
But if you think in perturbative string field theory,
right.
then I think yes, you should be able to talk about gauging, the gauge invariant operator that creates a loop of string at some point in space, where you define that loop of string in some gauge invariant way. I mean, you wouldn't want to compute with these things, but in principle, I think they should make sense.
Yes, it would be nice though to have one toy computation just to make sure that makes sense.
Yeah, I agree. Yeah. I had some conversations with Andrea about that actually, but yeah, I don't know. It's non-trivial to even to try and find one simple thing to compute it. Yeah. But, I mean, it would be nice to understand that.
Thank you.
Okay. So somehow this says that we can't. There's got to I mean, we know that in some sense these phi's. Oh, did something go wrong?
I think they'll reconnect.
I see. Oh, okay, they're back already. Okay. So this phi, right? So we know this phi can't really make sense, right? Because the theory is holographic, and so it's got to be approximate and so on. But on the other hand, as Sandeep said, right? I mean, in this room, everything, I mean, these things make a lot of sense, right? And so, we shouldn't be too fussy in what we ask for, right? I mean, we better at least be able to make sense of the physics in this room, even if it happens to be going on up here. So what I'm going to do in the lecture series,
Does it mean that making sense always requires a background metric?
no. Well, I mean,
all our experiments we interpret that way. I mean, to date.
yeah. Say that you take general relativity and you canonically quantize, couple of the standard model or whatever, you canonically quantize. Now that produces a theory which is it's an effective field theory. So it's only going to be defined in some energy expansion, but it's defined to all orders in that energy expansion, up to ambiguities in counterterms, which you can fix by doing these kinds of things, right? By looking at these correlation functions and doing matching, you can fix all of the higher derivative operators in the effective action from the CFT. We can talk about these gauge invariant operators, and they should make sense to all orders in that perturbation theory. I think that it's reasonable to ask if the CFT is able to reproduce that. I think if it can, we probably say the duality is wrong, right? So I mean, it should be able to reproduce that.
I mean, the notion of a local bulk operator is, I think also saying is almost certainly approximate, right?
Yeah.
And I think, does it fail only at e to the minus 1 over g, or does it fail even earlier? I'm not
So
certain.
I mean, most of the lecture series we're going to be understanding better, right? Like how good of an approximation can this be, and how do we deal with this problem? So, I mean, roughly speaking, the idea is that the operators there will be states where the operators make sense and states where the operators don't make sense. defined up to order e to the minus 1 over g. But they will be defined up to order e to the minus 1 over g, and not only to some power or something.
And then obey properties like the analog of commuting outside the light.
That's correct. Yeah, and that's
Or the light.
that's right. And we're going to discuss that at length. Yes. So, okay, and so, the whole goal of this, indeed, is to understand how the physics of that effective field theory of matter coupled to gravitons ordered by order in G can be, if you like, simulated in a formal field theory which is living in a lower number of dimensions. That's the real mystery, right? Especially this locality in the radial direction, right? Where, how do you think about that from the CFT point of view? So that's the main problem that we're going to try and address. We'll see almost that it can't. We'll almost prove that it can't be addressed, and then we'll see that if you're sneaky, it can. You can do it. Which, of course, I guess we expect because the CFT should make sense.
So the number of operators which will satisfy the space-like commutator vanishing in the radial direction will be small in some sense. Otherwise, it's going to
Yeah, that's right. That's right. Yeah. But we'll be able to quantify that. Yeah. All right. So let me now just. I'm going to start reviewing some of the details of how you think about constructing these things. But I first just wanted to make an aside about what CFTs we think of as being holographic in the first place, right? Because not every CFT should we be able to reproduce this bulk effective field theory. So I'll say, I'll say CFT is holographic if, one, there exists a bulk effective action for the metric, and then some finite set of matter fields, such that if we look at correlation functions of operators in the CFT, and so more carefully low dimension operators, that these can be reproduced by a bulk effective field theory with this effective action, and the appropriate operators here using the dictionary. To all orders in G Newton. So this is a perturbative statement. So order by order in G Newton perturbation theory. These two match. And it's clear that you certainly wouldn't in general expect the Ising model or something has a local bulk effective action which reproduces its correlation functions, right? So this is a very strong constraint on the set of CFTs. And to be honest, as an immediate CFT, we're really only interested in these CFTs.
These O's are bulk operators?
These are boundary local operators, but then they're limits of bulk fields from the extrapolated dictionary. That's right. Yeah. So basically, it's saying if we take the correlation function, this is for an order 1 number of O's. So it's saying you have some correlation function of some order 1 number of low-dimension operators in the CFT, and then using this effective action that's reproduced by the Feynman-Witten diagrams in the bulk, order by order in G. So,
and in your definition, you don't require S effective to be local or
no, I do. Yeah, this is a Wilson action. So there's some cutoff scale. So yeah, I guess maybe I should say I'm just thinking of the cutoff scale as being a word of the Planck scale. There might be a separation by G string or something, but I don't want to have to deal with that every time. So I'll just say therefore the same word, like Canadius 4 times 7 or something.
So do you require a separation of the scale of locality to the scale of AdS, for instance? in your definition?
Yes, yes. So this is an effective field theory, so it comes with a cutoff.
Okay.
I will always think of that cutoff as being the Planck scale.
Which is small compared to
Which is
radius.
small compared to the AdS radius. Yes, that's right. Yes.
The fact that low energy gravity theory is non-renormalizable, that will mean at some point you'll have to keep an arbitrarily large number of counter terms in your effective action. So
Yeah, that's correct. But remember, the CFT is unique, right? So we have a fixed CFT, and that'll determine all of those coefficients. So this effective action has higher derivative terms, all the way out. But once we pick a renormalization scheme in the bulk, then those will be fixed by matching to the CFT correlators. And the non-trivial statement here is that there's some choice which works, and that's not obvious. Okay. So then another thing which secretly actually is kind of a slight generalization of this is that the CFT statistical mechanics should agree with the black hole thermodynamics of S effective. And so these are if you want this statement to be true also when the boundary is S1 times SD times SD minus 1 or something, then this just follows from that. But I wrote them separately just so we can certainly I'll be assuming both are true in everything that I said. We can discuss to what extent they relate independently. Now, one set of CFTs which do have properties 1 and 2 was suggested by a famous paper by Keemskirk, Panagonis, Volchinsky, and Sully. So these are the so-called large N theories with a gap. And I know most of this is familiar with you guys, but I just want to get all the common language out at the beginning so that for the rest of the week we'll be on the same page. So here's what I mean by a large N theory with a gap. So there exists a finite set reimbursements I've been procrastinating. There exists a finite set of single trace operators. Let's call them O sub I, with the spins less than or equal to 2. The correlation functions of these guys to leading order in 1 over n can be computed by weight contractions. OI, J, OJ, OK, OL, plus symmetrization. The dimensions of these guys are order n to the 0. Actually, let me say it the other way. So the 3-point functions. So if we normalize the 2-point functions of these guys to be order 1. So if OO is order 1, then OOO is suppressed by some parameter which I'll call n. That's the definition of n. And the dimensions of these operators are order n to the 0.
So more generally, you replace n by the central charge?
Yeah, well, so in theory, yeah. So for example, in 2D CFT, this n will be like the central charge, yes. But I mean, I didn't say anything about gauge theory though. So this n, if you like, is the central charge. But I don't want to use that language because that's going to follow from so the stress tensor is always going to exist, and then demanding this is going to imply that. Yeah.
What do you need the first condition?
What?
Finite number of single trace operators.
A finite number of single trace operators, because I want to rule out things like the slave theory.
No, spin less than y on spin
I
less
said less than or equal to 2. Because say that there was one where the spin was 3, then you would have a light spin 3 field in the bulk. So I'm trying to avoid that. I mean, it's not. I mean, we can. So as I said, I don't want to. I mean, again, I don't necessarily want to say that this is the only option. I said this is an example of a theory that obeys these two things. I mean, you can imagine, for example, you have QCD in the bulk or something, and you have some, baryon or something is spin 3 or something, right? I mean, so we can. I mean, several of the things here we can generalize. I'm just trying to give one set of criteria which is sufficient. I don't want to say it's necessary. Let me finish writing the list of criteria. So,
To clarify,
yeah,
you're saying that you aren't allowing any single trace operators with spin 3.
yeah,
Likewise.
yeah. I mean, right. So, then I want.
If the theory comes from Kaluza line reduction of the high dimension gravity, that's true.
Yeah.
Most of our examples.
That's right. Yeah, most of the examples are like that.
And moreover, we have good reason to believe that if you do allow a higher spin field, then you probably need a tower.
That's right. Yeah, right. That's right. So that's right. That's why I want to not get into that. Yeah. Now, and of course, with the KKs, though, that also violates this because I said finite here. So then I have to weaken this to a tower. I mean, so. Yeah. I mean, you should think of this as being like something like, like if you take a quotient of, some supersymmetry preserving quotient, or something where you do a compactification which is small, some Calabi-Yau or something.
But no, finite is just you just put in an extra condition.
What?
Why should it be finite?
Well, I'm just saying.
He's giving an example.
I'm just giving an example. I'm not telling you. I'm not telling you it's necessary.
You want to make another example?
Why specifically?
I think in the back of his mind, he has a theory which would have a gravitational dual which has a few fields.
Yeah, that's right. I'm just trying to reproduce the kind of bulk effective field theory we see around us, right? I mean, we can always then generalize, right? We can say, oh, there's really a large S5 and there's a tower of K modes and so on, but I mean, right? There's not in our world, so. Okay. So let me say the other two things. So then, so for any set of these guys, OI1, OI2, there exists a multi-trace operator, OI1, OI2, with dimension delta I1 plus delta I2 plus order 1 over n. So given any two single trace operators, I can multiply them to get a multi-trace operator, which is also primary, and whose dimension just comes from addition. Okay, and that's it. That's a very strong requirement on the CFT. Most CFTs are absolutely not going to have this property. Okay, and then finally, all operators with delta order 1, or so let's say order n to the 0, are single multi-trace primaries, handwriting is terrible, or their descendants. All right. So yeah, and then if you have all four of these things, then it was argued in this paper by Himshirk, Penonis, Pensky, and Sully, that that's sufficient to imply the existence of this S effective in the bulk. And the way that they argued that was by, if you assume you know all of the operators, the low dimension operators, then you can try and solve the conformal bootstrap, right? You can try and determine the 3-point functions of these O's, then you try to match. Basically, you argue that you can, you parameterize the set of all solutions of the bootstrap for these operators, and then you match those parameters to the parameters appearing in some bulk effective action. And then you see sort of roughly speaking, the numbers. So a solution of one problem gives you a solution of the other problem.
And just to ask about that, I mean, when I read the paper, which was a long time ago, I remember being not completely understanding the cutoffs they put on the two sides to match that.
Yeah. So there's some right. So
Is that totally? Do you feel it's a totally kosher?
I would say that is not a totally solved problem. I would say that they gave I review their paper as making it seem very plausible that these problems map onto each other, but there are a number of technical issues they didn't deal with. I mean, they only dealt with scalars. They were a little bit careless, about how exactly you cut off and so on. Right. There's a question of extending to loops and so on. So there was just a paper recently, actually, by Ofer and Eric Perlmutter at UC, which did some of this at one loop. But yeah, I mean, right. I mean, there should be some theorem here about CFTs and bulk-effective actions, and it's not quite that level yet. But we're going to assume the existence of this theorem for the rest of these lectures. Certainly, it's very plausible. Okay, so I'm just going to restrict to, for the most part, thinking about these kinds of things, at least in conversation, just so we all have something, specific in mind to talk about. Yeah, I mean, as was already mentioned, there are several things that wouldn't fall into this category, right? So you could have a KK tower. You could imagine that there's some other coupling in the bulk which is less suppressed than gravity, right? So like in our world, there's electromagnetism. Alpha is only 1/137. That's pretty big, and so then that would mean that this 3-point function being small wouldn't be true, right? Because there were just electromagnetic interactions would contribute to this at a much bigger scale than gravity. So I mean, you could dress all this stuff up to include these possibilities, but I mean, it shouldn't be too mysterious.
But do we know if there exists any theory with these properties? I mean, in the sense that any theory such that it's the large end limit of something that exists in finite with all these properties. We have an example of something, a real example of something.
Yeah, so I think that so for example, if you do KKLT pre-uplift, it should give you an example of this.
We don't know the field theory dual, sadly.
You don't know the field theory dual, but I think we're pretty sure it exists. I mean, because the construction makes sense in string theory. Everything is reasonably under control. Yeah, you just do string theory compactified on some supersymmetric small Calabi-Yau with negative cosmological constant.
And the size of the Calabi-Yau is arbitrarily small.
Yeah,
it is
There's
much
a parameter.
smaller than it would be.
much smaller than the AdS radius.
There's some parametric separation.
Yeah, I would say, so usually what I imagine in the back of my mind when I'm thinking about this is we have the Planck scale, and then we have some string scale, which is lower than that by some order 1 amount, like say 10 to minus 3 or something. And then at that scale, we have some compactification, maybe it's a little bit bigger than that to give us large volume control, but maybe another 10 to minus 2 or something. And then effective field theory is way below that. And so by chance you should expect to find those sometimes, I guess. I mean, you have to say by chance to solve the cosmological constant problem.
And far be it from me to take away from KKLT, but if you believe in massive 2A, some people who are purists may not, but if you believe in their even simpler examples, I would say massive 2A of non-Freud Rubin, which are AdS.
It would be really nice to have one field theory example.
Yeah, okay.
We really know what
So even in the massive 2A, the field theories.
Yeah.
None of the non-Freud Rubin, the field theories are. But I was just saying, if you wanted constructions, which are
until you have both sides of a duality with one clear example, you're never really sure these things exist, right? There could be nothing wrong.
Yeah.
Well, should be. I mean, are there cases where you start with something where there's a big extra dimension and then you do some supersymmetric orthofold or something? I don't know.
But just to say, I mean, there's a lot of evidence that supergravity as such is a theory which exists and so in its domain of validity, and they're totally reliable supergravity constructions which are supersymmetric, which give you non-Freud Rubin AdS spaces. And so, okay, the duals are not known, but I would be very surprised if they didn't exist.
How much supersymmetric?
Is there a question? Subhan is saying something. What?
I think the only discussion here is whether you're willing to include the
unifying tower, I just didn't want to write it. I mean, it's just kind of a pain. I mean, the methods I'm going to use later kind of don't really take it into account, but I think they could easily be generalized and taken into account.
Right, but it won't matter for anything you say, we just include the Kaluza.
Yeah, I think it wouldn't matter at all. Yeah, it wouldn't matter. It's just, I mean, when I write equations, involving integrals over all of space, and I say that they're d plus 1 dimensions, then I'm sort of, I would have to modify those equations a little bit if I wanted to include the S5 or something. But I mean, sure, it'd go right. Easy to do, I think. Yeah.
But Shiraz, if you include the Kaluza criteria, then of course we have.
Then we have a
Then we have lots of
Yes.
That's right. I'm right. I'm just trying to save myself some writing. I don't think it's a deep problem. I mean, well, it is a deep problem, but not for me.
Yeah, okay. It would be really interesting if you had one example without supersymmetry. Whether something like this exists without supersymmetry,
But
that is brilliant.
so there are people who say it doesn't, right? I guess
People say it, but I don't think
That's
it's
buffer
saying
and,
that.
yeah, yeah.
That would be the equivalent of solving the cosmological constant problem.
Yeah,
If you
that's-
get one example without supersymmetry.
Right.
It would be the equivalent of solving the cosmological problem if there was no string scale in between string scale and max.
Well, I mean, to be clear though, so I mean, there is a, so I think the cosmological constant problem, roughly speaking, is solved. But it's solved for positive lambda, right? Because it can be solved in a metastable de Sitter vacuum. But there's no such thing as a metastable AdS vacuum, right? So that's the.
Okay, we can go to this, but I mean, just to say, I mean, I would agree with Surat, right, that if we could find a example, non-supersymmetric example, we would need to have the AdS scale bigger than some cutoff scale, whether you call it Planck or string scale, I mean, it doesn't much matter because that's the scale of the gap, right?
That's right.
And I think...
I mean, I agree, this is solving the AdS cosmological
Yeah.
constant problem.
If
I'd be
loops-
surprised if it really exists without supersymmetry,
Well,
actually.
if loops are suppressed by G string, and G string is the smallest scale in the problem,
Yeah.
then there's no cosmological constant. Right? I mean, if you've got some cutoff at alpha prime, and then that cutoff is suppressed by G string, and that G string can be made smaller than anything else, then
Sorry, but why shouldn't you generate a cosmological constant at the string scale?
you generate it, but it's suppressed by G string.
Yeah, but G string is not that small, right? I mean, so G string is 10 to minus 3 or something. I mean, it depends what, I guess, what we're doing for particle physics, right? But
That's another question. But I'm talking about just an in-principle thing. If you take the limit G string to 0,
yeah.
then it's less clear that you're solving a cosmological constant. I think it's really clear that you're solving it in a case like M theory. In a case where you've got this M theory kind of compactification, where you don't have an intermediate scale between string scale and tensor. You've got one of these compactifications like that.
But I mean, we also want the AdS radius to be big in
Of course we
units,
have.
though,
Of course
right?
we have.
How
Of
are
course
you
we have.
going to keep the AdS radius big if G string goes to 0? I'm not sure you can do that.
AdS radius between G string goes to 0, like n equals 4 angles.
The R to the 4 is G string n alpha prime to the 4. So if you take, I mean, I'm not sure what you have in mind. If you take G string literally to be very, maybe you want to scale.
I mean, there's an Achuf, I mean, in the Achuf limit, G string goes to 0, right? So I usually don't like to think about holography in the Achuf limit, but if you do the Achuf limit, then you think of lambda as being order 1 and n being large, right?
Okay.
So then G is going to 0 in such a way, and n is going to infinity in such a way that lambda is order 1, but large.
Okay, so that's, but in that case, I suspect that the loop corrections are governed by the 12th coupling, right?
The bulk loop corrections will be suppressed, will be cut off at string scale, and then we'll have G factors of G string, because they're bulk loops.
Yeah.
So they can be made arbitrarily small.
But I think naively you expect to generate a cosmological constant at the string scale, though.
At the string scale,
Yeah.
with factors of G string.
Yeah, yeah.
And if you take the limits G string strictly goes to 0, we can talk about this.
Okay,
Yeah.
that's an interesting point. Okay, I hadn't thought about
Yeah.
At AdS scale,
Yeah, sorry, what's your rock?
you would also get a very large star of particles at the AdS scale in this setup. I mean, this would be some. Is that right, Shiraz?
Oh, sorry, I didn't hear your question. Could you say it again?
In the setup you're mentioning, you would also have a very large number of particles. It wouldn't have this property that Daniel mentioned, which is that they're very small, very few light particles.
In the setup I mentioned. Yeah.
No, Shiraz wants to have a setup where, sorry, where
But
the
is it-
string scale is higher than our AdS,
Yeah, so I mean, when you're
but
in
G
these,
string is very small, right?
And lambda is order 1, right?
I mean, n
Lambda
equals,
is order 1.
I mean, n equals 4 in the
Yeah.
AdS limit does not satisfy my assumptions because there are stringy states. So lambda is morally order 1, and then there are stringy states, right? So that's why so the limit I like is that G string is small but finite, and then n is large.
Yeah, the flat space.
The flat spacing.
Yeah, let me just say what I mean to Subrat though. I mean, if you find a non-supersymmetric version of ABJM theory at a large n and large k with n by k held fixed, it's not clear to me you solve this cosmologically constant problem. But if you find a non-supersymmetric version of ABJM theory and n goes to infinity with k held fixed, then it's totally clear you solve the cosmologically constant problem.
Because that's an M theory.
That's like
Yeah.
I think that's because there's no other scale in the middle.
Yeah.
Then you gradually look at off by only one scale, then you clearly solve.
Yeah.
Okay.
All right.
That's interesting. Interesting stuff. Okay. All right.
It's a cultural aside.
Right. Okay.
Okay, as long as everybody's happy. Okay, so that was all I was going to say about this question of which CFTs are holographic. So from now on, I'm just going to assume we have a holographic CFT where there's a finite number of all fields. So let me erase this because so if everyone's happy with this, now I'm going to move on to analyzing that. All right, now Subrat can really go to sleep. So now I'm going to I'm going to discuss explicitly the simplest case of how you think about representing this bulk field. So just in the case where you have a free scalar field, and you're working in the vicinity of the vacuum, so the geometry to leading order is just AdS. So free scalar near vacuum. So to the extent that this is a good approximation to something, right, then it means that some coupling is weak. So say in the previous discussion, n is large, and then being near the vacuum is some restriction on the states where we're going to use these operators. So
Is it bulk scalar?
bulk scalar, yeah, bulk.
And okay, no, I'm just making sure. Okay.
Yeah. So okay. So then the idea. So then there's going to be an algorithm. So we want phi of r, t, and omega. So omega is always the angular coordinates on the sphere. Such that so this is we want a CFT operator labeled by a point in the bulk, such that if we act on it with the equation of motion, we get 0 as an operator equation. So this is an operation acting on the labels of the operator in the CFT. And then we want this extrapolate dictionary that I wrote before. So R, T, and omega. Then we get the CFT operator, which is dual to phi. And then the point is, well, hey, this is a PDE, and these are boundary conditions. So let's just solve it. So we're just solving a PDE, right? That's all we're doing. We're solving an operator value PDE. Okay, so let's just quickly remember. So then in the vacuum, the metric is like this. The R squared.
So you just forget that it's operator value, right? Solve it where it was guessed.
Yeah, dude. If you like, just solve it matrix element by matrix element. Yeah. And then you see the boundary condition though is an operator value boundary condition. So then the solution
So
will
some
be
Green's
operator
function.
value. Yeah, that's right. So we're going to solve it with using some Green's function.
I thought you would just solve it as you normally do in terms of some node expansion. function where the coefficient would be operators.
We're-
and
yeah,
identify the-
We're about to do that. Yeah, we're going to do it that way first, and then we're going to do it the way with the Green's function. Because to go to so we're going to include interactions by the time we're done, and then the Green's function is a better way to think about it. Okay. So this is the metric. And then as Sandeep just suggested, we can just whatever this solution is, we can look at it in Fourier space, right? So we can expand it as a sum on n, l, m. Then there will be some radial wave function psi.
To solve this equation, you need some initial conditions. You need to know what's happening at the early times.
Well, we'll see to what extent we need to know that.
This is Minkowski, right? It's not Minkowski.
Yes, we're always in Lorentzian signature. I'm a Lorentzian kind of guy. I'll draw this picture here, although Subrat can't see it, but he doesn't.
Oh, but you're saying if you know what's happening here, you don't.
Yeah, think of it like a Dirichlet problem in electromagnetism, right? I just need to know things are non-singular here, and I'm going from the edges. All right. So then the solution now be a sort of
Is it
radial.
anything that starts at very early time will show up at the boundary at some time?
Yeah, that's right.
Therefore,
Whatever's here, it gets out.
Yeah.
So, yeah. Okay. So there will be a radial wave function. There will be some frequency, time dependence. We can have spherical harmonics. Then this will be multiplying some operator coefficient, A n L m. And then we'll have the complex conjugate. So then we just need to identify what is this A n L m in the CFT, and then we've identified what is this phi in the CFT, because the rest of this is just the classical solution. And let me comment, right? So this omega and L is delta, the dimension of the operator equal to phi, plus L plus 2n, where n is 0, 1, dot, dot, dot. So the frequencies are quantized. That's because this is essentially a Dirichlet problem. We have a particle in the box. So the energy levels are quantized. If you like, that's because this psi has to simultaneously have the right fall off at infinity and be not singular at the center. Right? So that picks out discrete frequencies. Then this delta is given in terms of the mass of the particle, the way it always is. Okay. So then the point is that we have this extrapolate dictionary here. So we can look at the values of this psi at large R. So the boundary conditions tell us that psi in L of R at large R goes like some C number normalization factor. I'll call it script n and L times R to the minus delta. We know that there's R to the minus delta and R to the minus D minus delta. And so the boundary conditions are that the coefficient of the R to the minus D minus delta is 0. So then we just have this guy with some coefficient. There are no sources, yes. I never want sources. Sources are always 0. I want to understand the theory. Hilbert space is the theory with no sources. Okay. So then this means that O of T and omega must be equal to sum on n L m, this normalization factor, e to minus I omega n L T, y L m of omega, a n L m. Okay. So just took this equation again, and I took the limit R goes to infinity, and then plus the complex conjugate. So then if I define the Fourier transform of this boundary operator, O of omega Lm, which is integral dt minus infinity to infinity, integral d omega, e to the I omega t, y Lm star, omega O of t phi delta of omega minus omega nl a nl n. So because the frequencies are discrete, most of the time for most omega we just get 0, but then we pick up delta function contributions as we move it across the discrete frequencies that are appearing in the Fourier transform. You might ask why I didn't just do the integral from, say, 0 to 2 pi or something, and pick out directly the discrete things. But the problem is that the bulk field isn't really periodic under time 2 pi unless delta is an integer, and I don't want to assume that. I want the masses in general to be arbitrary.
Discreteness comes from the boundary condition at the origin and at infinity.
And at infinity, that's right. Yeah, and at infinity. You have to satisfy both.
I see. So like in the AdS 5 plus S5 case, the deltas do turn out to be such.
Yeah, so in the supersymmetric ones, they often end up being integer quantized, but that's kind of, we don't want to commit to that.
The Cauchy operator will not.
Yeah, but that's not in the supergraph.
Yeah, I mean, right. So
This is really coupling.
Yeah.
Enormous dimensions.
I mean, it may be that I'm being unnecessarily general because there are no non-supersymmetric examples or whatever. But I mean, I don't want to get into that debate.
Yeah, once you include interactions, anyway, this
Yeah.
will be covered.
Yeah. Well, unless there's some non-normalization theory, which is true in those cases, because the operators are EPS. Yes.
So for the
Yes,
I
right.
can't see the code very well, but you have the limit going from minus infinity to infinity on t. I can't see that.
Yes,
Yes.
minus infinity to infinity. That's right.
But you could just strip off the e to the I delta t part, and then you would have an integral from there.
Yeah, but the problem is that there's an e to the I delta here and an e to the minus I delta in the complex conjugate. So then you can do that, but then you have to split phi into positive and negative frequency modes and then separately reconstruct them, which is kind of annoying.
Okay.
So I didn't want to do that. Yeah.
but once you include bulk gravitational interactions,
Yeah.
the whole gravitational solution will not be periodic anymore.
Oh, that's true. Yeah. Yeah. Sure.
So
Yeah. That's right. Okay.
So in principle, you could do this even if there's a black hole sitting in the middle, so that the boundary conditions in the interior would now be different.
Right. So we could try to do this with a black hole. The metric would be different.
Yeah.
I'm right. I mean, yeah. Most of these manipulations would go through, but I mean the details will be different. So let's hold off on it. Yeah. Okay. Good. So now what this tells us is that right. So this gives us a relationship between A and O, and now we can just sort of back substitute this back into our original equation for phi, replacing the A's by O's. So if we do that, we find the following thing. We find that phi of R and T and omega is equal to the integral over dt prime from minus infinity to infinity. The integral over d omega prime of something that I'll call k of R, T,
just go on.
T prime, omega prime, O of T prime, omega prime. So where this K is called the smearing function, and it's given by integral d omega sum over L and M, and then psi omega L R, e to the minus I omega t minus t prime, y L M of omega y L M star of omega prime. Okay, so I kind of did two steps at once here, but you can check that if you take this k and you stick it in here, and then you do the integrals over t prime and omega prime, that takes the Fourier transform of this O, and then using this, it comes back to being this phi. Okay, so another problem. So this this gives a representation of this bulk field phi at any point in the bulk in terms of an integral only over boundary points of the operator O at those boundary points, but then against this kernel, which is this so-called smearing function. And okay, and integral is really over the entire boundary, right? From t goes minus to infinity, and omega. All right. Now, one interesting feature of these kinds of formulas is that this choice of k is not really unique, because there are definite. So in this O, right, we had only these quantized frequencies appearing to this leading order in the interaction, so the free case. And so since you only have certain frequencies appearing, if you stick into the integral over t, into k, things which integrate to 0 against those frequencies, then it doesn't change the left-hand side of the equation. So then by, for example, sticking such factors into the left and right moving parts separately and so on, you can fiddle around with what this expression is for k. So I derive the one which sort of conceptually is the simplest. But it turns out that actually when you try to generalize interactions, there's an alternative choice which makes life a little bit easier. So I won't go through the details of how you can fiddle with this one to turn it into the other one, but the result is that you can choose an alternative k, where if here's your bulk point, let's just call it little x, then you can arrange for this boundary integral to actually only have support over points on the boundary which are space-like separated from little x. So there's an alternative choice of k. And actually, we'll discuss in a minute actually one way of how you can derive it. But so it says that phi of x is equal to the integral over the set of points which are space-like separated from x on the boundary. This is d big X. We'll comment on this convention in a sec. Right. So I'm going to introduce this notation here, which is a little bit unfortunate when you try and do it on the blackboard, which is that capital X's correspond to boundary points and lowercase x's correspond to bulk points. So then the claim is that there's an alternative choice of smearing function where when you integrate over the boundary points, you only have to integrate over this space-like separated set of points, and you can and it'll be equivalent to what we did here. So this is and this is the version of the construction which is most widely quoted. So you've probably heard about it. So let me just.
And so somehow you can just take this and show that the other regions which are time lag separated don't contribute. Or?
Yeah, that's right. You can just play. You can fiddle around with these things here by adding things which integrate to 0 against O, and then by the time you're done, you find that you've arrived at this formula where this thing is just 0 outside of the.
Because of this periodicity, it's sort of clear that if you know what's happening at the boundary in a band of size 1, you know everything.
Yeah, that's right. So if you're willing to, so if you're willing to write a formula where there are two separate k's for the positive and negative frequency parts of O, you can immediately, even just using these kinds of techniques, you can arrange for the integral to be over a strip of width 2 pi. And so actually, usually what you do is you first do that, and then you do this thing where you
But I thought
arrange
you
it
were
to.
not assuming the periodicity, because that's only true if the spectrums of some time, right?
There's an overall thing, and then there's on top of that there's a periodicity.
Yeah, maybe this is a good way of saying it. So again, let me tell you one way of constructing this. So what you do is you start with the point in the center, and then you do the construction as Shiraz suggested, where the integral is over a strip of thickness 2 pi, and where you choose this guy to be sitting at t equals 0 in the bulk. Okay? So then in that case, it happens to be now the case that it's space-like separated.
I'm really sorry. Why can you restrict the integral to be in a strip of 2?
Oh, because the frequencies are quantized, right?
But that I thought was not true in general.
And
Right?
there's an overall
phase from this
Doesn't
delta, which kind of doesn't matter from the point of view of projecting out. You can still project onto the coefficient. You pick up this extra annoying phase.
Oh, I see.
So you're saying basically there's only one irrational number in the case, that's right?
Yeah, there's only one
You have
possibly
two
irrational
operators.
number around. Yeah, if there were two, then you'd be out of luck. Yeah. That's right. Yeah, and then once you have it in a strip, then the idea is now, if you put the point in the center, then by doing conformal transformations, then it kind of moves the strip around to produce these kinds of things.
I see.
So that's one way of
Okay, so
constructing
while
it.
but just to understand, while it's in the strip, at least the edge points are still connected. I mean, rather, you're still including points which are space-like connected, time-like connected, right?
Yeah, but right.
Then you
have
do
to
your
do a
conformal.
little, you do a little bit more to make
Okay.
it so that it's space-like, and then you do the conformal.
Okay. Thank you.
Daniel, not to make too fine a point of this, but you mean space like and null?
Oh yeah, I'm kind of agnostic about that. Let's say space like and null. I think I'd probably better say and null. Yeah, I think we'll get into trouble if I don't.
Yeah, and just to say, I mean, the normal case of Green's function is a solution in terms of the source. The source is totally arbitrary, so you don't have this kind of freedom. Yeah, because it's not source; it's just what the solution's becoming at the boundary, and that's constrained by the equations of motion. That's why you've got so much freedom.
Yeah, that's right. So I mean, I think this is a sort of the most intuitive way of constructing this, but it's a little bit tedious from the point of view of trying to turn into this kind of thing and so on. So actually, what I'll do now is.
Can I ask?
Oh yeah, sure.
So you had an operator equation in the bulk. You must be
Yeah.
assuming some commutation relations that the operators, commute outside the.
Hold that thought. We'll discuss that at the end of the lecture. Yeah. So far, I'm not actually. I'm just solving the operator equation. Yeah. But in the end, I better make sure that the algebra works out right. So we'll discuss that. Okay. So that's all I was going to say about the free case. Let me now discuss the interactions. And then that should also clarify some of the things that we saw here. All right. Yeah.
So I'm just trying to think about which other area of physics I've seen this before. Is that you take some part of a solution and you produce the rest of it. Sounds a bit like Huygens principle. You take away front and then you integrate together the rest.
Yeah.
Sorry.
Yeah, I mean, somehow you're using the fact that you know that only certain frequencies appear.
Yeah, I know. You're using the fact that your boundary data is not arbitrary.
Yeah, that it's not arbitrary. That's right. Yeah. Okay. So now let's discuss how to generalize this to interactions. So now I'm going to use there's going to be a mathematical object that's going to be very convenient to talk about to use, which is called a space-like Green's function. So let's say what that is. So let's space-like. Space-like Green's function. So the idea is we've got some function, which is a function of two bulk points. So this is little x prime. And we want it to have the property that if we act on it with box prime minus m squared, then we get 1 over square root minus g of x prime delta g plus 1 of x minus x prime. So of course any Green's function obeys this. That's the definition of a Green's function. It's the bulk Green's also going to demand that g of x prime is 0 if x prime are time-like separated.
It's the reverse of the usual.
Yeah, so it's the opposite of the usual.
Yeah.
Yeah, that's right. And maybe I'll just comment on that now. So a priori, it's not obvious that there should be Green's functions like this. One way to think about it, at least in AdS, is that if you put one of the points at the center, and you imagine taking the derivative with respect to the other point, then by symmetry it reduces to a 1 + 1 dimensional problem. And then in 1 + 1 dimensions, if you just rotate by 90 degrees, then it is the usual causal problem, so the solution has to exist. And then by using a symmetry, you can now get it where the 2 points are at arbitrary points.
In flat space, such a Green's function would not exist.
Well, I think the set of words I just said would still all be true, right?
And what about using a symmetry?
Well, you use the Poincare symmetry instead of the conformal symmetry, but it still acts homogeneous.
So it's
It
possible.
acts transitively on the space.
So I think one way of thinking of a Green's function is you hit with the source and you measure the response.
Yeah, that's right. But then there's a question of what are the
What are
boundary
the
conditions?
conditions?
Yeah.
So let's say there's some solution which you tune to where your source is, such
Yeah.
that there's nothing in the future of the source, for instance.
Yeah, that's right. So somehow, so from a Lorentzian point of view, this is a very weird Green's function because it's somehow saying that somebody is sort of sitting at the boundary or something, sort of playing with the sources to make sure that whatever you do, kind of nothing comes makes it into the region which is time-like separated from this point.
So we could write out just in flat space for the operator L squared plus n squared. We could write out the Green's function.
Yeah, that's right. I think we could just write this down.
I mean, in flat space, I thought it's not, because the only choices are retarded, because you know that you can move the I epsilons in 4 ways.
Yeah.
That's the only choice. So it's retarded, advanced Feynman, or anti-Feynman. That is anti-time order.
And none of these.
And none of them will have this property.
Unless you break translation in bed.
Yeah, no, the symmetry, so in the construction I just described, the symmetry won't be manifest. Because I put something in the center, I constructed it, and then I said I take that and I act on the symmetry so only a subgroup of the symmetry will be manifest, right? Whereas in the ones you said, it's sort of the symmetry is manifest, right? I mean, it's got to be true, right? Because in the boundary conditions, in principle, you can put all sorts of stuff that breaks the symmetry. It's just usually we don't think of that as being allowed. But here there's some, if you like, some combination of the symmetry violating things which actually has the symmetry.
So your function won't be a function of x minus x.
It won't be
It won't just be a function of
invariant.
Yeah. So actually, right. So in
Translation, even
Yeah.
translation won't even be translation.
So
X minus
somehow in AdS, so I thought about it a lot more in AdS, but actually there's this funny even odd thing where, so like we're right with massless things, right? There's this funny even odd thing where
delta on the light
sometimes
cone.
stuff is just on the light cone, right?
Yeah.
And those actually obey this, right? Because that was part of why when Subrat asked, I said I have to allow also on the light cone to be non-zero.
Yeah, so in 4 dimensions it's clear in flat space it exists, but in 5 dimensions not so.
That's right. So in AdS, that's also what happens. So even I don't remember who's even.
Even is light cone or is not.
Yeah. Okay. So in even, but then we do d plus 1. So okay. Anyway.
Work is light cone.
But right. So people have constructed this explicitly for even and odd, but for the odd one, it's kind of the symmetry is not manifest.
Okay, interesting.
And actually, it's a very interesting problem to construct these in geometries which are asymptotically AdS but don't have the symmetries. Then it's not even known that they exist. We somehow, formally, they should exist, and by the end of what I say, it'll be clear that maybe there's some way of formally constructing them, but to convince a mathematician of that might be difficult.
But in AdS you can explicitly construct, right?
In AdS you can write down a formula, that's right. Yeah. So in this, I meant to say, so in this discussion I'll be following this paper of Klimt's, which is Hume, Skirk, Merolf, Polchinski, and Sully. So 3 out of 4 are the same as the previous paper, but Penedonis got replaced by Merolf.
Is this a recent?
This is 2012. Yeah, and so there they have the formulas for these things. Actually, I think their formulas for the odd case are wrong. I had some correspondence with Jamie Sully about it, but the existence proof is correct, so it must exist. But I think that maybe only believe the explicit formulas for the even case.
which are very simple formulas.
Which are very simple formulas. Yeah, it would be worth probably somebody going through and cleaning up the odd dimensional case. I think the formulas there are wrong. I'm not worried about the existence. Okay. All right. So from now on, I'm just going to assume that we have one of these space-like Greek functions. So let's start by writing a formula that seems obvious. So phi of little x, well, it's always going to be equal to integral over the bulk, square root of minus g of x prime, d of x prime, and then we can just take this box prime minus m squared, acting on g of x and x prime, phi of x prime. Okay. True equation, right? From this, we have that. But okay, now we can be clever though, right? What we can do is we can integrate by parts this guy to move it from acting on g to acting on phi. So actually so we can rewrite this as an integral. So I guess before I called it S sub x, the set of boundary points which are space-like separated from x. So now
it's kind of manipulations that Jackson does about.
Right. These are Jackson knows about these manipulations. Yeah. So now we have an integral over big X prime, which is the boundary point, square root of what I'll call minus gamma of X prime, which is the induced metric on the boundary, and then so R mu is the sort of radial normal vector, and then we get d prime mu acting on g times phi minus g times d prime mu acting on phi. So that's the boundary term from the integration by parts. This is kind of like the symplectic current, if you like, although it's not quite the same because there's a g here instead of variation. And then there's a bulk term where we just integrate over the bulk d little x prime square root minus g of little x prime, and then we get g times box prime minus m squared acting on phi. And then so in the free case we can drop the second term by using the equations of motion, but now we're going to want to do interactions, so we have to keep the term. Now let's first work out the boundary term. So we know that phi of little x goes to r to the minus delta times O of big X. That's this extrapolate dictionary again. And moreover, since g of x and x prime in the limit of large R prime is a solution of the wave equation, then we can expand it. So there'll be some coefficient, which I'll take to be 2 delta minus d. And then there'll be a part that goes like r to the minus delta, r prime to the minus delta, times some function of big X prime, little x, plus some thing that goes like r prime to the d minus delta, times some function which I will call k of little x big X prime, and then be symmetric. Let me switch these as big X prime. Okay, so that'll be always true, right? We're just expanding the solution asymptotically, and we know we're going to get these two powers of r prime. But now if we substitute these asymptotic forms into this boundary term, then sure enough, we discover that phi of x is now just, was there a question? Okay, with integral over s sub x dd x prime, now we get a square root of the CFT metric. So remember, the CFT metric and the induced metric on the boundary differ by a factor of r squared. So this is now the CFT metric, and then we get voila, this k function times O of x prime. So we get the same thing that we wrote before, except now we have this extra interaction term.
You don't get anything from the L, is it?
Yeah, so the L, because the L is subleading. So here, yeah, so it's important here, so this is the fast falling mode and this is the slow falling mode. Now technically that means I've taken the branch of delta which is bigger than d over 2. And so then if you want to do the alternate quantization, we have to shuffle things around a little bit, but the story doesn't change in the end. Yeah. Okay, so then, and then now we've still got this bulk term, so now I'll just write it more heuristically as d little x times box prime minus m squared phi times g.
In electromagnetism, del phi and phi were independent pieces of data.
Del phi and phi.
You know, you had two terms here. You had a phi and a del phi.
Oh, you mean here?
Yeah.
Yeah.
But here, since you know how phi behaves near the boundary,
That's right.
they're really the same piece of
That's
data.
right, they're really the same piece of data. Yeah, that's right.
In Jackson, though, you know, he keeps both terms, and then you have to choose a Green's function that either vanishes or whose gradient vanishes.
Yeah, that's right. So what we would say if we were doing it working at finite cutoff,
Yeah,
is we would
at
say
finite
that
cutoff.
we're imposing Dirichlet boundary conditions on phi. Yeah.
Right.
And then right. And then the equation of motion in the vicinity of the boundary will relate.
It would be
to,
related to del phi, not
Yeah.
phi.
Yeah.
But here, of course, it's all the same.
Yeah. Okay.
In the surface contribution, so you took only the component from the boundary,
Good.
but there could be a surface contribution also from the light one, no, or not?
No, because we started with the integral over the entire bulk, right? So then what we're left with is then the boundary term. So strictly speaking, that right, if I do Stokes' theorem here, what I get is the integral over the entire boundary. But then this g and del g it vanishes except at space-like or null separation, and so then that restricts the integral. Yeah. And that's why the space-like Green's function is so convenient, is that there's not a boundary term in t equals plus or minus infinity, where there would have been had we used a causal Green's function. And of course that would be a pain in the butt because the extrapolate dictionary doesn't help us down there, right? So we want to have a space-like thing that we know exactly what to do with phi. Okay, so now we're cooking with gas, and we can and it's now pretty clear what we how to keep going to higher orders of perturbation theory. So to have an example, let's say that the equation of motion is
Dan, maybe you could plan to finish in the next 10 minutes for today,
oh yeah, sure, okay,
because we get late for lunch.
okay, yeah, sure, that's fine. Yeah, I mean, I think we're pretty close to the punchline here. Okay, so let's say that the equation of motion is that box minus m squared acting on phi is some coupling g, and okay, since we're assuming it's a large n theory, I'd better put a 1 over n here. So it's some coupling g, which you can think of as order 1 divided by n, times phi squared. Okay, the simplest phi cubed interaction as well, right? Well, okay, so then we can take this equation and we can substitute here. So now we just get g times phi squared. I mean, there's a prime. So we get that phi equals to something involving O plus something that's of order g over n. So then you do the obvious thing, right? You iterate the equation. So you take this form of the equation, the left-hand side, and you substitute it in to the phi squared that you get here, right? And then now the leading order thing will become from when you have two of these guys there, and then you can keep going. So that tells us. So I'll just write out the first non-trivial correction. So phi of x. So there's the part we've just been discussing, which is like integral of k times O. And then now there's a new part, which is like g over n times integral. Okay, so now this will be the most painful equation to write. So d big X prime square root minus g CFT of big X prime. Maybe I'll drop the square root of g's. I guess we're all adults, right? So then there's a d big X double prime. So now there's two boundary points because there was a phi squared here, so there's two of these guys. And then there's also a bulk integral, the little x prime, coming from here. So three total integrals. And then we're going to get, well, what are we going to get? So we'll get two k's. Right? We'll get a k which is like from x here to, which what am I saying?
Two bulk to boundary property.
Little x prime to big x
Yeah,
prime.
but it's prime. Yeah, it's from little x prime to big X prime. We'll get a k from little x prime to big X double prime. Right?
And a g.
And then we'll get a g from x to little x to little x prime. And then we'll get an O of big X prime and an O of big X double prime. So we can think about this diagrammatically. And then that makes it obvious what the rules are going to be in general. So there's a leading order piece where we have a k that connects the boundary to this point. And then this term is like this. There's two boundary points. And then connected, so here's little x, here's little x, right? And then, and then here's little x prime and here. And then clearly we can keep going. And generate a representation like this to all orders in the interactions.
That line, little line is G, right? There are two big lines coming from the boundary, and those are the two K's, and then there's a Green's function G.
Yeah,
There are
good.
two different
Yeah.
lines of
There's a capital G here, and there's a K and a K.
So those lines are
Yeah, that's right. Yeah,
Every Green's function in the game is non-zero only in this space.
yeah, it's space-like separations. Yeah, that's right. Okay. So now let me just make a few editorial comments, and then we'll be done for today. So the first comment, well, we ended up discussing it already, so let me say it a little faster. But this ends up involved. This is solving a non-standard Cauchy problem, right? So if you because well, I never remember what means hyperbolic and what is elliptic, but we're not doing whichever the good one is.
We're not doing elliptic, yeah.
Because time is going up, but we're solving the equation this way. So actually it's neither hyperbolic nor elliptic. It's some one of these mixed things. So if I go to talk to PDE people about it, they get very unhappy.
And this is
Oh, I see. I thought you were going to say, sorry. I thought you were going to say we are not solving the Green's function problem for a elliptic operator, which is clear because box is not a elliptic operator. But
But it's not hyperbolic either, right? Because, so I think elliptic, so the only way I can remember this, so one of them which I think is elliptic is the one which is like the Euclidean Green's function.
Correct.
Right? Like the electrostatics or something,
Yes,
that's
yes.
elliptic.
Right.
Hyperbolic is like Lorentzian time evolution.
Yeah.
But we're doing neither of those things because we're, in our initial conditions, there's a Lorentzian direction, but then we're evolving in radially. Okay.
And this is probably the reason that our data was constrained.
Yeah, that's right. Yeah.
If you're doing hyperbolic, then you can set whatever initial data you want.
Yeah, that's right. So
the boundary conditions are.
Yeah. Okay, now I understand.
So in fact, when I talked to a PDE expert, Mihalis Stefanos, about this, he was so outraged at the concept of solving the equations this way that he said AdS CFT must not make sense.
And you said, come on, be a little.
I said, come on. Usually when you need some non-trivial, when string theory wants some non-trivial mathematical thing to be true, we know what usually happens.
You have an explicit formula for this G.
Yeah, so in the vacuum we do, but I mean this procedure we would think it should make sense also like if there's a planet or something or in some other asymptotically AdS geometry. I mean here we kind of cheated because we use the symmetries of the vacuum to turn it into an ODE. And then that makes life easy. But in general you're not going to be able to do that.
Your doubt is that you are able to do it with purely space-like separations.
Yeah. Now I should say that, let me just say formally though, right, so if you had some state which you got, with some planet or something, formally you could build that starting with the vacuum and then resumming the infinite series of these. And then somehow formally that has to construct this thing, right? But I tried that one on Mihalos and he wasn't happy, so.
But just to understand, you're saying if your state itself could be constructed with the appropriate boundary conditions,
Yeah.
that is your seeing it.
Yeah, I mean, it's like, right, it's like,
It had better come out of this form.
right, I mean, it's like an electrodynamics with a hydrogen atom, right? You can either have the proton in the initial state, or you can say there's a classical field, right? And of course, the correct thing is that the proton is in the initial state, and you use the vacuum propagator, and then you resum a bunch of stuff, and then miraculously, or maybe not miraculously, you find that you can get away with the electrostatic approximation. So the same thing should be true here for constructing this thing in general, but okay, that's words, no one has actually done that. All right. Okay, so that was the first comment. Second comment, you see that at higher orders in the interactions, the operator is becoming more and more non-local, right? Because we get more and more of these integrals over the boundary. So and that has to be true, right? Because although this operator is local in the bulk, from the boundary point of view, its representation is going to probably be quite complicated.
Wait, even at lower, leading order is quite non-local.
Well, right. So in leading order, yeah, that was going to be the next comment. So it's local as a space-time integral, but if you try to view it as an operator at t equals 0, it's a very complicated operator because you're sort of taking the Heisenberg field at some other time and representing it at t equals 0. It'll be some non-local mess. So these operators, although the formula isn't that bad, I mean, if you really think about like how would I represent this operator in terms of the spins, the fundamental, gauge fields and stuff at t equals 0, it's very complicated. Okay. Now the third comment, which is related to what Spenta asked an hour ago, is that this. I mean, I constructed operators that obeyed the bulk equations in motion, but how do I know they're the right bulk equations in motion? Right? I mean, how do I know that they're actually the right? Say I mean, this G was just a parameter here, right? I mean, we could take the Ising model and I could write down this formula. And it would give me an operator which obeys the extrapolate dictionary and obeys the equation of motion that I put in. But I mean, come on, that can't really be right, right? So what this construction so far hasn't promised you is that the correlation functions of these will actually be the right correlation functions in the bulk effective field theory. I haven't promised you that, and clearly that's only going to be true if I use the equations of motion that came from the actual bulk effective action that we were discussing earlier. So Kabat and Lifshitz actually, Kabat and Lifshitz studied one example of that, right? So they showed that if you, say, just look at the 3-point function, so like say you look at sort of phi, O, O, so then that'll have some contribution that comes, if you just use the leading order expression, there'll be some contribution that comes from the 3-point function of O in the CFT. And this will have some coefficient. And, well, clearly this coefficient should somehow be related to this coupling constant in the bulk, right? And indeed they showed that if you use this formula, you have to pick the right value of this G in order to preserve space-like commutativity in this correlation function, right? You want this phi to commute with these O's if they're space-like separated. And it won't in general if you just put an arbitrary G here. You have to put the right one that comes from the CFT 3-point function.
And I'm sorry, it's obvious that if you put the right one, it doesn't. I mean, the bulk construction makes it obvious that this becomes a commuting object.
Good. So yeah. So right. So it's obvious if you assume AdS CFT is correct, right? So remember, I promised. So my definition of AdS CFT was that being correct was that the boundary correlation functions of local operators are reproduced by Feynman-Witten diagrams from the bulk theory with some effective action. If that's true, then those boundary local operators are all that appear on the right-hand side of this equation, right? So it must be that if I use the right equations of motion for that effective action, then these guys are going to have the right algebra, because I'm just reproducing the calculation of the bulk effective field theory with that effective action.
So now I'm very confused.
Yeah.
Let me get this right. See, I thought because you sort of solved for the bulk equation of this operator phi of x in terms of the boundary data, you're going to get a field which will vanish, which will commute, which will meet the right right commutation properties.
No, not necessarily. I said it has to obey. I picked the bulk equation. I said here are the bulk equations of motion, and I wanted to obey them. But I mean, I have to make it. If I want to get the algebra and the correlators right, I better solve the right bulk equations. So if I solve the ones that come from the effective action, whose Feynman-Witten diagrams reproduce the correlation functions of O in the CFT, then it's clearly going to work. Because then you can just interpret all the right-hand side of this as being, facts about that bulk effective field theory.
I mean, but just from the consistency of the logic,
Yeah.
you can get the O correlators using your extrapolate dictionary from the correlators of phi, right?
Well, but we're trying to find phi. We don't. I mean, we started in the CFT. O's are all we have, right?
Okay.
So the idea was I want to construct an operator in the CFT. So it's kind of self-consistency.
Yeah.
I said, imagine that there's an operator phi in the bulk,
Okay.
which obeys the extrapolate dictionary and obeys the equation of motion.
Okay.
Then it has to be this operator.
Okay.
But there might not have been such a phi, right?
Okay. Okay.
And there won't actually be unless well, I mean, sorry, to be clear, I mean, this phi always exists because I can just write this formula.
Yeah.
But its correlation functions won't be the right correlation functions for bulk effective field theory unless I pick the right coefficients here coming from the right effective action.
Okay, and just to understand, when you say it won't be the right correlators for the bulk effective field
I
theory,
mean, for example, commutativity of space-like separation will not be true.
it will not be true
Yeah.
unless G is related to the correct coefficient of the OP on the boundary.
That's right. Yeah.
But I think Sandeep is saying that now you take this formula for phi
Mm-hmm.
and use that to compute the OPs of O's.
Yeah. that's
Because
what
you know what O is in terms of phi.
Yeah.
And that will give you a formula for 3-point functions of O in terms of this G.
Yeah.
So then you plug in this G for that OP.
Yeah.
But it might not be the right one, right? I mean,
just from the
I never took an expectation value here anywhere, right? I just wrote an operator equation. So the only input from, I mean, so far the only thing we know is that the O here is the local operator in the CFT, which I said was dual to phi.
I agree that you need to use the consistency of the sort of logic,
Yeah.
but you could do it two ways. You could say there's a G here, and I'm going to assume that the bulk operator becomes a boundary operator, etc., and compute a 3-point boundary correlator in a consistent way in terms of G.
Yeah.
Or I could say there is a 3-point, which is I think what you're saying, I see
Yeah.
how you're coming here, that there is a 3-point correlator in the boundary, and I'm going to use that to fix G.
Yeah, yeah.
All right, I see your point. But I think it's kind of interesting for me that even something like commutativity outside the light cone fails. It
Yes.
wasn't obvious to me that is what would fail if the logic didn't hold.
But I mean, I didn't say anything about I didn't use the algebra of the O's at all here, right? Because, I mean, I just said that it obeys this equation. I mean, I just said phi has to obey this equation. And this equation by itself isn't enough to tell you the algebra of the operators, which is a classical equation. So, I mean, you somehow have to do canonical quantization, right, and so on.
So you're saying that it doesn't really depend upon my choice of the kernel very strongly. These kernels must be very important in reproducing this.
I mean, this equation, if you like, is really just a fact about PDEs, right?
Yeah.
And it's just a way of representing the solution.
I mean, that's what I was saying. That is what I.
Yeah.
So this is obviously correct.
Yeah.
And then you fix G in terms of 3-point base or the other round.
Yeah.
It's still okay.
But then the claim is if you do that, you must get a set of phis which have the right correlation functions for the bulk effective field theory. Because the only thing that goes in on the right-hand side is the boundary data. And we already know that bulk effective field theory gives you a set of operators which have the right correlation functions. They're consistent with that boundary data. So this must be the same as that.
For this statement, it wasn't important that you use G's that was space-like commuted. That were not the only space-like.
No, I used that just in the derivation of this equation.
But you could have used some other G's.
No, but there would have been boundary terms in general, right? Because if there's boundary terms at t equals plus and minus infinity, then there will be additional terms in this equation.
Okay, suppose I use some G that extends past the space-like separation but vanishes at
Oh,
large.
yeah. It just has to vanish at sufficiently large time.
And then any of those G's.
Then any of those G's